everybody. It is now time for our feature presentation. And I must admit to you that we have done a bait and switch on you tonight. You see, we have claimed that this talk on extraterrestrial intelligence was put together by our esteemed program chair, Dr. Dale Partin. Actually, we have the true author of this talk who wants to share his insights with us. Come on. Come on. It's okay.
Objection.
Overruled.
You scared him. So now you will have to speak through the esteemed Dr. Dale Partin.
I used to hold you in high regard.
See you at the Recto, Gary.
Don't you have somebody else to do tonight?
Actually, I'm wearing my disguise now. That's my brother you just saw. How many people here are willing to admit that they're really an alien?
You're
I see
a
guys.
Sorry.
Phil certainly.
Let me say a couple of things about this presentation. Number one, when I give a presentation on extraterrestrial intelligence at DEFCON 1, it will not be the same as what I'm presenting here. It will be a little more on the science fiction side, at least some elements mixed in with it. Secondly, I gave a presentation right here, I believe it was about 6 or 7 years ago, on extraterrestrial intelligence. Some of you were, I'm sure, here for that. And so I call this an update. A lot has changed in the last half a dozen years. Partially because of new discoveries that have been made, a lot of that, and partially my perceptions of this field of inquiry. And I'll share a little bit about that tonight. An outline is, I'll talk about exoplanet discoveries. I'll also talk about searching for extraterrestrial intelligence. There are a lot of gaps, even today, in our knowledge about this. I think I don't have to tell people that. And so, filling in the gaps so that we make estimates for what the chances are of finding ET, we use guiding principles. On the optimistic side, there's what's called the principle of mediocrity. And kind of on a little more the pessimistic side, there's the anthropic principle. I'll explain both of those. And then there are a couple of equations, an old equation by Frank Drake, and a newer one by Sarah Siegel, that are used to estimate chances of detecting life or intelligent life. I'll try to reserve a little bit of time at the end for discussion. Let me say, do not expect certainty. Just enjoy the topic, right? I mean, this is part of why we're in the hobby of astronomy. It's a fantastic, it's not like bowling, you know? I mean, that's one of the things I like about astronomy. It connects us directly to major fields right at the forefront of modern science, one of which is, what's the status of looking for and potentially finding life, maybe intelligent life, in other worlds. So enjoy it. Just enjoy it. Let the chips fall where they may. Stay tuned. This is a rapidly developing field of science. I'm not an expert. I'm a kid at the seashore. I think we all are on this topic, at least. That's the reality of this topic. And I think that this topic is huge. A lot of the things I will talk about tonight, the whole presentation could be on one slide, and I'll just expand on that. There are major things I won't be talking about. So I just was selected how much I could cover. So, there are two dominant methods for finding exoplanets, planets that orbit stars other than the sun. Potentially that includes planets that don't orbit any star. The one that until recently was dominant, and it still is very important, is based on the Doppler shift. Here you have a star with a planet going around it. So the planet, obviously, it orbits the star, so it makes a big orbit around it. But as the planet orbits, the tiny gravity of the planet affects the star and makes it wobble back and forth. So there are gases on the star, like hydrogen, that emit light at very specific wavelengths. And if you measure with extreme precision those wavelengths, you can see them shift back and forth as the star comes toward us and then wobbles away from us due to the gravitational pull of the planet going around it. And you can measure the velocity of the star toward us or away from us to within 2 meters per second. I mean, I can run that fast for a star that normally moves at very high speeds. That's an incredible resolution, sometimes even 1 meter per second. I can walk that fast if I work at it. So that has been a dominant technique until recently. There is a spacecraft called Kepler, which collected data for 4 years up until a little over a year ago, when it had some mishaps. It's still collecting data, but in a little different mode now. And the way it works is the Kepler spacecraft just stared at about 100,000 or 150,000 stars for years. Just continuously stared at the same stars. And if a planet came along and happened to have its orbital plane edge on to our direction of view, you would see, you can't resolve the star and see a black dot go across the star like Venus transiting the sun, but you can see the light from the star dip down slightly. This looks like a big dip, but it's frequently a very, very much less than 1%, less than 0.1% kind of dip. But with the Kepler spacecraft, it was possible to measure the light of the star with incredible precision, so you could see these tiny dips. So that's another way of detecting planets. Now, when such a dip was observed, you could not be sure that it was due to a planet. It could be a sunspot, for example, or a star spot, I guess, for something other than the sun, that's rotating around the star just like the sun rotates. So when the Kepler spacecraft would see one of these things, they would say that's a candidate planet that needed to be confirmed with another technique, typically with the Doppler technique. And if such a planet that seemed to transit a star was then also observed with another technique such as Doppler, then it changed from being a candidate planet to being a confirmed planet. This is a very important distinction for where I'm going in the next couple of slides. So, the problem is, it's been very laborious to go from these Kepler candidate planets to confirmed planets. A new insight came out early this year by some of the Kepler scientists. It is that when stars with multiple transiting candidate planets are seen, so at least two possible candidate planets going on the same star, it is very unlikely that this is caused, for example, by multiple transiting stars. You know, 3 or more stars orbiting each other that can transit each other. Since that would be an unstable system. Now, you could have a close binary star system, 2 stars orbiting each other very closely, orbited by a more distant third star, and that can be stable. But you cannot have 3 stars at comparable distances and comparable masses. That's not stable. Conclusion, just announced in February this year, stars with multiple transiting candidates are automatically considered a star with multiple confirmed planets. This kind of shows you pictorially what I just said. Ordinarily, if you have a star being orbited by planets, such as our solar system, the mass of the star totally dominates the gravity in that system. Even a Jupiter has gravity, a tiny, tiny fraction of the gravity due to the sun. Its mass is tiny compared to the mass of the sun. So to a first approximation, each planet, if it doesn't come too close to another planet, has a motion determined almost totally just by the star, by its gravity. So they're stable orbits. However, if you have a collection of stars orbiting each other with roughly comparable masses and roughly comparable distances, all the studies that have been done by mathematicians, by physicists, astronomers, whatever you want to say, indicate that you simply cannot get a stable orbit. You can only do that, as I said, if 2 of these stars are very close together, a tight binary couple, and then maybe another star way out orbiting them. Okay? So, up until February of this year, this was the story of detection of exoplanets. There's number of detections per year versus the year. So this is what's called a histogram, and the color shows you which way each of these planets was detected. Up until Kepler, the Kepler satellite came along recently. The main detection was red, which is this radio velocity or Doppler technique. And then when the Kepler spacecraft went up, those results are in green. You can see that it became, for a while, dominant. Note that the maximum detection rate was something like 180 detections per year. Okay? Something changed after February 26th. Here the scale is different. Here's 180 detections per year. All of a sudden, after February, we're up to almost 800 detections this year in February, right? That's a big deal. Almost doubled the total number of exoplanets confirmed. And the way they did it is, in every one of these cases, there were at least 2 detections per star with the Kepler spacecraft. So, all of a sudden, we have 715 newly verified planets orbiting 305 stars. If you double 305, that's 610. So, 2 or in some cases 3, for example, planets orbiting each of these stars. So the total number of planets goes up to about 1,700, and multiplicity, observing 2 or more transiting planets per star, is now a self-confirming technique. And all the results I showed here are just for the first 2 years of Kepler's observations. The spacecraft worked well for 4 years. So you can bet the mission scientists are real busy crunching the data, and I can't wait to see what else they find. So, not all planets that are detected are good places to have life. Here's a star, and depending on how much energy it's putting out, there is a green zone, a habitable zone, at a certain distance from the star, where if a planet orbited in this habitable zone, and if various things work out well, it would be at a nice temperature for life. Mostly what that means is these days, most scientists are willing to assume that you need liquid water for life. It's always been known that there may be other possibilities, that non-water-based systems where you might have life at higher or lower temperatures. Some people speculate there could be life living in liquid methane mixtures on Titan, for example, the moon of Saturn. But for the most part, the greatest hope, at least, is for life in a liquid water system. And so, depending on the reflectivity of the planet, if you assume some reasonable reflectivity, you can calculate how big the zone is, depending on the type of star. For a red dwarf star, the habitable zone would be real close, like this. But if a planet has an orbit like this, that's highly elliptical, then it's a fire and ice situation, right? When a planet is in this part of its orbit, it's fire. It's too hot. And then when it comes out here, everything freezes up. The example I showed, this ellipse has an eccentricity of about 0.7. A perfect circle has an eccentricity of 0. The Earth has an eccentricity of about 2%. For those of us who live in the Northern Hemisphere, it's a surprise to many people that during our winter, when it's obviously cold, that's when we're actually slightly closer to the sun. Okay? That's not the cause of seasons on this planet. It has to do with the tilt of the Earth's rotation axis, is what dominates our seasons. So, here's a collection of data from all techniques for detecting planets. This is the eccentricity versus the length of the planet's year. So, where is the Earth here? Its eccentricity, here's 0.1, so 0.02 roughly would put the Earth down here somewhere. The length of our year is about 300 or 400 days, so the Earth is right about there. Some of these planets that have essentially 0 eccentricity, that are very, going around in one day or less, are probably tidally locked to the planet, like the moon is tidally locked to the Earth. So the same side of the planet always faces the star, which means it might get too hot on that side and too cold on the other side. And you might just have a ring of habitability around the terminator of the planet. So, messages, many exoplanets have eccentricities higher than something like this. Who knows exactly how big it can be, but something like this, where they probably are poor candidates for less likely places for life to exist. This is another plot showing the transit depth. When you see when Kepler sees a planet transit another star, this is parts per million. So 10 to the 4, 10,000 parts per million would be a 1% dip in light from that star. Most stars have much less than 1% dip in light. And you can pull out the radius of the planet from how big the dip was. So some planets that have been seen have a radius similar to the Earth. That's hopeful. There are various reasons. If you think life on such a planet is going to be roughly like life here, that you might want the planet, need the planet to have a size comparable to the size of the Earth, because the Earth has plate tectonics that recycle the Earth's crust, and that can do some healthy things for life on the planet. Now when you have a big volcano or earthquakes, so in the short term it can be bad for life, but longer term it can be very good. And the geologists think that it's more likely to have such a healthy geology if you have a planet roughly the size of the Earth. Another issue that's obviously important is what's the average temperature? This is on the Kelvin temperature scale. 0 degrees Kelvin is real zero. You can't go lower than that. Our temperature here on Earth, the average temperature is 287 Kelvin, which is somewhere in here. That's 57 degrees Fahrenheit, average temperature of the Earth. So this box shows, planets that might have temperatures roughly at least comparable to those of the Earth. Here they've expanded that box, and I put in a cross where the Earth is. Problem with these calculations is they assume that you know what the albedo of the planet is. That's sort of a fancy word for how reflected it is. Venus, for example, has a very high albedo compared to the Earth. So the albedo of the planet can vary a lot, and that would affect its temperature. There are many, I'm just giving you tiny little pieces here. There are many of the story. There are other problems you can have with such calculations. Here there was a news item back in January, a planet that had been discovered where it was possible to measure not only the size of the planet using Kepler, but also its mass with another technique. Found that even though it has the same mass as the Earth, but it's 60% larger in diameter. Okay? And that means its volume is 4 times bigger than the Earth. So its density is only 1/4 of the Earth's density. So this would be a planet that's enormously different from the Earth, even though its mass is about the same. And density is only known for about 150 exoplanets, which is, I calculated, about 9% of the planets so far confirmed. on a larger scale, where is extraterrestrial life, or even just plain life, most likely in our galaxy? The galaxy has what some people have called a habitable zone. And you don't want, it's less likely, you can never say never, but it's less likely that you'd find life in the nucleus of the galaxy. Stars are way too dense there. Interactions with planetary systems would cause frequent catastrophes. If another star passed close to our star system, to our star, it would disrupt the orbits of our planets, for example. And way out here on the edge of the galaxy, stars have low density and low metals, heavy elements like oxygen, carbon. So less likely to have terrestrial type planets like the Earth, rocky planets. So in the habitable zone, stars orbit at about the same rate as the spiral arms of the galaxy. So you don't have periodically, every 10 or 20 million years, I'm speaking a little crude here, but a spiral arm come racing through past the sun, sending all kind of debris into our solar system. The Earth is close to being in the habitable zone of the Milky Way. Now, that's the story for just, looking for planets that might be suitable places to live. And there's an enormous amount of work yet to be done there. Knowledge is just exploding. It's a fantastic time to be in this hobby where you can kind of be tuned into what's happening. But you can kind of leapfrog over all of that if you can detect directly signals from intelligent life, either radio signals or possibly optical signals, for example. So there's a scientist, an astronomer named Frank Drake, who started trying to detect alien radio signals back in 1960. He was an astronomer at a big radio telescope. And until that time, and those of us who were around back in the 50s, like me, may remember this, talking about extraterrestrial intelligence was mostly something in comic books and science fiction books, okay? Scientists who would talk about this had to be careful lest they risk their reputation, okay? There was a major change in what was respectable science, started, in essence, by Frank Drake. It's not that no one had ever talked about such things before him, by any means, but he really, I would say, you could kind of choose him and his beginning studies in 1960 as kind of a threshold where this became respectable science. He called a conference, invited some people to it, let's discuss this. Carl Sagan was one of the people that came. A dozen years later, Carl Sagan predicted, 1973, that a signal from extraterrestrial intelligence would be found within 10 years. 10 years. Okay? That sort of came and went. And it did. I mean, I think it's important to not lose the history of this because you learn something from it. My perceptions changed when I saw this pattern. Carl Sagan, great scientist, did a lot of work in popularizing astronomy and space travel and things like that. And he died without any detections. Scientists can live and die waiting for these 10-year prophecies to be fulfilled. Looking back on it, there's just a huge amount of optimism that went into these predictions. I know two people that sat in his classrooms and heard him make these predictions in this time frame. And now, Dr. Shostak is head of the SETI Institute, Search for Extraterrestrial Intelligence. I guess institute is kind of redundant with the I here. He has taken, to some extent, Carl Sagan's place in promoting these ideas. And, searches with advanced equipment, searches are now 100 trillion times more effective than they were back when Frank Drake started all of this. 100 trillion times more effective. Back in 1999, I bought a set of videos by Dr. Shostak back in the early 2000s, like 2002 or something. And he mentioned that in 1999, Frank Drake predicted detection within 10 years. So I heard this back in about 2002 or 3, and I thought, okay, I will remember this. And I remember year after year, no detections. 10 years later, it was 2009. Frank Drake has been an optimist from day one. And let me say, I went through a period of being very negative on Sagan and Drake for being wildly optimistic. I'm not so negative on them anymore. You've got to be optimistic about whatever it is you're doing, right? Or you wouldn't even try. And I really think it's worth trying. Funding has really been cut to places like the SETI Institute. And I really regret that. They even had to shut down this facility of theirs for a while, something like a year ago, because they just didn't have enough money to keep it going. Last I heard, it was up and running again. I'm not as optimistic as they are publicly, because I've seen these 10-year things come and go, and I'm not getting any younger, and they aren't either. Frank Drake is now pretty much retired. He's 84, okay? But why 10 years? Why are they always saying 10 years? I could understand it if there was a track record of detecting an intelligent civilization 20 years ago, and then 10 years ago, and boy, we ought to be detecting another one about now, right? But there isn't anything like that. So I think I get it, finally. And this is part of my update, my own perception of these 10-year predictions. If they said within 3 years we'll have a detection, that would be all over the place, big news. People would remember that for 3 years, right? People would remember. Even 5 years. I think people would remember. 10 years, it's far enough in the future that it's kind of safe. And most people don't remember. I heard on National Public Radio, their Science Friday program, this is something like a year ago. They were interviewing, what is the guy's name? Ira Plato? What is it? Plato. He went to the SETI Institute and he's interviewing people there about this topic. And he first talked to one of the junior astronomers there and asked him, how long do you think it's likely to be until we get a detection? And the guy, I was surprised. No, he said, 50 years, maybe 100 years. And Plato was surprised, right? Because he's heard these 10-year things over and over again. And he said, well, I'm just being honest, you know. It could, maybe it'll be next year, but it could be 100 years from now. And Plato was like, whoa. So then he talked to Seth Shostak, who hadn't apparently heard what the okay? And he came out with the standard, well, I think within 10 years.
Oh, God.
So Plato sort of gently challenged him with what the other guy thought. I hope the other guy didn't get fired as a result of this. And Plato really pushed him and got him to say, Seth Shostak, to say, well, there's no guarantee that there's intelligent life anywhere else in the Milky Way galaxy. But I hope there is, and that we find it within 10 years. I mean, I'm trying to be, on the one hand, realistic, right? I mean, I just heard 10 years for too long. On the other hand, I have to say, you got to be optimistic to even try, and I think it's worth trying. And what he may think privately might be different from what he says publicly. Because you need supporters to keep this stuff running. So that's part of my update, my perception of why it's usually a 10-year thing. Now, I'm going to pick up the pace here. What are the principles that are used to fill in the gaps in our knowledge for making estimates? Well, on the positive side, there's the principle of mediocrity that says there's no reason to think that there's anything special about mankind.
Amen.
That is to say, we are presumed to be mediocre. Principle of mediocrity, right? Some of us are a little more mediocre than others.
You shouldn't speak about yourself. If you've got any place else to be, can't.
Okay, so there are two reasons used to support this principle. One is, it doesn't look like the place we are is special in any way. A long time ago, we figured out we're not at the center of the solar system, we're not at the center of our galaxy, the center of anything, right? Well, I would comment that nowadays, being at the center, those kind of arguments are sort of archaic a little bit. We wouldn't want to be at the center of the Milky Way galaxy, right? That's a bad place to be. Secondly, a second supporting argument for this is it appears that life on Earth started quickly when the Earth became habitable, that is, when it cooled down enough to have liquid waters, within a few tens of millions of years, not all that long compared to the 4.5 billion years of the planet, life started. Therefore, even though we don't know how life started, and nobody's figured it out yet, but it did happen, so one can assume, reasonably, that life starts quickly everywhere when environmental conditions are right and frequently leads to intelligent communicating civilizations. I would add something that's usually not said here. You not only need good environmental conditions, but they have to stay good for billions of years to get from primitive life to intelligent communicating life. Mars would be a case study of a planet that might well have had primitive life for a while, but not long enough to have time with good environment to get complex, intelligent species. On the negative side, there is the anthropic principle. It's not totally on the negative side, but sometimes it's used that way. The universe, our universe, seems to be finely tuned for intelligent life, and especially for life on Earth. This was first noted by Paul Dirac back in the 1930s. Very bright guy. He was the first to figure out a relativistic version of quantum mechanics, and he predicted the existence of antimatter long before, because it came out of his equations, long before anybody else did. Won the Nobel Prize for that. An atheist, by the way. We're not talking about intelligent design here. Then, a few decades later, an important astrophysicist, Robert Dicke, said, you know, we've discovered a lot more things, amazing coincidences, he called them, that make life possible in our universe and on our planet. And he, also an atheist, by the way, believed that an unknown law of physics must be involved, not intelligent design. Nobody has discovered such an unknown law of physics. There are a lot of factors that seem to make our universe a nice place for life. I don't have time to go into them. There are a lot more than these. I'm not going to go into it, but the usual comeback to this is to suggest, to claim that there's a multiverse of a nearly infinite number of universes, and this just happens to be a universe where things are finely tuned for life. Maybe so and maybe not so. There is no evidence of such a multiverse. There's zero. But there may be such a multiverse. Now, Frank Drake wrote an equation for calculating the number of intelligent currently communicating civilizations in our galaxy. I frankly don't have time to go through it. It has 8 factors that you multiply together, 3 of which we kind of know roughly, at least ballpark versions for some of these numbers, because they're physics and astronomy kind of numbers. The ones we don't know have to do with life. Fraction of planets where life actually does form, we don't know. Fraction of those where intelligence arises, we don't know. Where they start communicating, how long such civilizations communicate before they kill each other with whatever, nuclear weapons, biological weapons, something. Pardon me?
Objection.
Object later. I can't have my presentation hijacked, especially when I'm running late on time. Here's what Seth Shostak said back in 1999, this set of videotapes I bought of his. He put in numbers for all of these things. And he estimated, for example, that of all the stars, 10% of them form planets. His estimate was that meant 4 billion planets in our galaxy, and he came up with 4 billion planets where life forms. Okay, I mean, it just looks optimistic, right? And you know, half of those developed intelligence, all of those start communicating. They live at least 100 years because we've had radio for that long. If you do that, you wind up with maybe 20 intelligent, currently communicating civilizations in our galaxy. If human dispersal to the moon and Mars happens, then maybe we live a lot longer, in which case his number goes to 20,000 in our galaxy. Drake had estimated 10,000, Sagan 1 million, currently communicating civilizations in our galaxy. Now, I don't want to make Sagan look foolish. He lived earlier, and a lot less was known then. And these guys are optimists. Now, that's Frank Drake's equation, and here are his, extremely poorly known, wild estimated factors. Since then, Sarah Seeger, who I think, if I remember right, is at MIT, has come up with a different equation. She says, okay, forget intelligent life. Let's just calculate the probability of finding life. She'll take any life, primitive life. Any life in how long? 10 years. And here's her equation, and again, I don't have time to go through it all, but one of the factors, which I put in red as the least well-known, is fraction of observable planets that have life, okay? Her guess, and what can it be but a guess, is 10% of them. And she figures that 2 planets will be found within 10 years with life by studying just the atmospheres of the planets. You know, if you looked at Earth, you would see a large oxygen concentration, and that would be a strong evidence that there's life here. And she says, well, look, we're going to have the James Webb Space Telescope, much larger thing up in space that can do these searches. And Europeans are going to put up a very large, extremely large telescope for completion next decade to look for biosignatures of atmospheric gases on Earth-sized exoplanets. So, you know, that gives hope. So, I'm wrapping things up. We live kind of in a sweet spot in our galaxy, in the habitable zone between 2 spiral arms, studying nearby stars within a few thousand light years for habitable planets should have a high probability of finding new candidates. We're in a sweet spot, so are the stars around us. Okay? So if there is life, we're in the right place to look for it. That's a good thing. As long as we find some. If we don't find some, then ultimately that starts to become a negative. Why didn't we find some? SETI searches and other organization searches of these planets for signals should have a high probability of success if advanced civilizations are common in our galaxy. You know, Sagan talked about a decade, Drake talked about a decade, Seth Shostak recently acknowledged that intelligent life may not exist elsewhere in our galaxy. These results strongly suggest that any astronomer who wants to do studies in this area should not base his or her whole career on finding intelligent life. Now, how many years can you not find something? You need to have something else to do.
1 million.
Where you can publish and get funding and keep yourself alive professionally. But should be publicly an optimist and always observe the 10-year rule. That's what you do. I don't mean to be completely negative about this, right? I mean, there's reality of how do you get funding to keep yourself in business. So, the principle of mediocrity says there's nothing special, because we're not the center of anything and so forth. So intelligent life must be commonplace. Anthropic principle says there is something special about our place, not about being the center of anything. Depending on how special our place is, and we're working on that, and we're learning like crazy, you know, 10 years from now, we're going to know tons more. Probably in the next year or two, we'll know a lot more when the rest of the Kepler data set is released. That's coming soon. So intelligent life could be much rarer than some have said, or non-existent in our galaxy outside the solar system. That has to be at least on the it could be list. With new satellites to be launched over the next several years, many exoplanets will be discovered. It's not just the rest of the Kepler data set. There's another major satellite that will be going up soon, within the next, I forget, 2 or 3 years. That'll do a lot of nice studies of this stuff. And a lot of these exoplanets will appear, as far as we can measure, to be suitable for life. The principle of meteorography assumes that life will be there. Okay? However, don't forget, even if it is, developing complex life forms requires environmental stability for billions of years. You know, the dinosaurs got wiped out by an environmental catastrophe, and that could happen to an intelligent species too. And look, maybe we already found evidence for life elsewhere on Mars. This just came out this February. A meteorite was found that, from studying it, it came from Mars. And when people cracked it open and looked at it with a high-resolution microscope, here's 2 microns, you can see these sub-micrometer tunnels. And so people are studying what caused those tunnels. It could be a natural process. It might not. I mean, natural means non-biological. Or maybe some little microbe did that. I haven't heard more since this was announced, but I think we would have heard if, or will hear, if this turns out to be due to living organisms. Okay? If it is, the question will be, is it really alien life? Right? There's exchange of material between the Earth and Mars, kind of in both directions, easier to go from Mars to here. It may be that it's Earth life or that we are Martian life, you know, I mean, who knows? I mean, it may not be really alien life independently started, is what I'm saying, if it's life. So, we live in a golden age of astronomy and of science in general. Knowledge is exploding. Whether you are an optimist, cautious, or a pessimist on this subject, the next couple of decades are going to be filled with discoveries. Enjoy.
You can guarantee that.
Dr. Partin, will we find intelligent life in 10 years?
Yes.
How much do you need?
What?
Funding?
Should we take a collection of 5, like I said many times.
You should have brought your hat.
Intelligent life find.
Why did they always use radio astronomy to communicate with an extraterrestrial life? I mean, what is the speed of it compared to the speed of light?
The same.
It's the same.
The question is, why would extraterrestrials or us use radio waves to communicate long distances? What's the speed of radio waves compared to the speed of light? It's identically the same if you're in vacuum in outer space. Identically the same. Radio waves are the same stuff as light, it's just at a longer wavelength.
Okay.
It's electromagnetic radiation. And you don't have to use radio waves. Some searches for extraterrestrial intelligence are looking for rapidly changing laser beams, for example. It's just harder to do that because of technical reasons. Yes?
Don't you feel that these are 2 completely separate, and not separate, but completely different issues? Intelligent life or life, period.
Right.
I mean, one presupposes the other, obviously, but whether or not there's really life, which is the basic thing we're trying to, I think we have more of a handle on, or intelligent life that could communicate with us as we're looking for at SETI in the time window of our own lifetime, or 100 years or 1,000 years, as opposed to the millions and billions of years that windows that may have, life may have evolved on this planet or that planet or that planet, may have
okay.
come and gone, and we may have come and gone. We
To
have
give other people a chance to ask questions, let me,
Sorry.
sure, I mean, the two studies are related, right? You have to have at least life before you can have intelligent life. But it would give people a lot more hope that there is intelligent life somewhere, even if we can't detect it, if they find even primitive life.
Exactly.
Right? Yes, Ken?
There's a factor involved in the mental picture of a human being that is actually in any other animal species on this planet is curiosity. When you talk about life elsewhere, I sometimes think of it as a dart. Because if you throw a dart and you get something like us, for example, we are biologically identical, really close to a tree, I mean, in our genetic makeup, as opposed to what would develop somewhere else. And they have to get to the point where they would have to be curious, not water bound, all kinds of other things. I'm kind of skeptical about it. There's a difference between intelligent life and successful life. You have a lot of successful life that's advanced on this planet.
Yes.
Well,
Look,
successful
the
and
dinosaurs-
communicating, I mean, it could be that
Well,
we
again,
are ultimately
I'm wondering,
unsuccessful.
how would you talk to somebody something that was genetically so different from you than a tree, and talking to them about morals or talking to them about laws or government?
I like ravens' survival chances a lot better than ours, and I like cockroaches much better than ours.
Well, yeah,
So cockroaches may not be intelligent, but they're definitely successful.
But again, to communicate with them is a whole different number.
I mean, dinosaurs are still here, and they outnumber us by a lot.
I'd like to take more questions. Yes, Alan.
About 100 years ago, we didn't know there were other galaxies. About 30, 40 years ago, we didn't know about extremophiles, organisms living at really high temperatures and living at the bottom of the ocean off of the vents from the gases coming out of the earth. We don't know a whole lot about life, let alone intelligent life. Some people have said there could be silicon-based life. So the possibility of life is not necessarily going to be like we know it. We may not even recognize it. I mean, as a good example of not recognizing it, look at the Horta from Star Trek, the rock creatures.
Objection!
That call was
I'm not going to take time to respond to that. Yes, Phil.
Just one other point. There's two major considerations. One is speculation, and the other is scientific proof. As you know, I'm a scientist, you are too. Proving a speculation is something entirely different from intuition or whatever have you. My intuition is the galaxy and the rest of the universe are full of life.
Yes, absolutely.
Intelligent life also. Proving it is another thing.
Okay.
I have an actual question.
Make it 30 seconds or less.
All right, with the sniffing the atmospheres for proof of life, I mean, you could say, oh yeah, that's good evidence, but would they ever actually be able to conclusively say there's no other way to get this amount of oxygen or whatever? You could never say it's not a natural process.
I mean, technically you're correct. However, oxygen is such a reactive gas that detecting roughly 20% oxygen content in an atmosphere strongly would suggest that something must be continuously producing it. And how do you produce such a reactive gas? Nobody, in such high quantities, nobody knows a way to do it other than through light. Regarding silicon-based life, the things I've read say the chemists have tried to look at how you could get the complexity of DNA in a silicon-based molecule, and they've had difficulty seeing how that could happen. But they've got more work to do.
Alrighty, that will be the last question for tonight. We're a little bit over time. If you would like to continue this discussion or any other, we head down Woodward to just north of 13 miles to the Red Coat Cabin.